Dear students, welcome to the next lecture of electrical measurement. Now, in the last lecture, if you recall, we discussed the different types of standards. Okay, so uh, in different types of standards, we had studied, or rather, we had seen that there are four categories of standards. The first one was the international standard, then we have the primary standard, then we have the secondary standard, and at last we have the working standard, and this was also the decreasing order of in their accuracies. Okay, now we'll move ahead uh, after this different types of standards. We know that all electrical measurements, they are based on the fundamental quantities like the current, resistance and voltage. We are talking about the electrical measurements only. So now you see that these three represent the current, resistance and the voltage. So if you just measure uh, anything, if you want to measure anything, so a systematic measurement, actually it depends on the definitions of these quantities. Okay, and we also know that these three quantities are related with each other by the Ohm's law. Okay, which is nothing but V equals to IR. So it is you can say sufficient to define only two parameters to obtain the definition of the third. Hence, what we do in electrical measurement is we can just, it is possible to assign the values of the remaining standard by defining the units of the other two standards. So generally at the national laboratories, the standards of EMF and resistance, they are being maintained. So the standards of EMF and resistance are maintained at national laboratories. Okay, so if you just recall that the primary standards, they are being maintained at the national laboratories. So generally the standards related to the EMF and resistance, they are being maintained at the national laboratories. Now we come to the voltage standard first of all. So or you can say EMF standard, both are same. Okay, so in the voltage standards, there are different standards like the primary standard, the secondary standard, the laboratory standard. Okay, so the figure which you are seeing here, this is the primary, you can say, standard, and this is nothing but a saturated Western cell. Okay, so this is actually a primary standard. Okay, so this saturated Western cell acts as the primary standard of voltage or EMF. So the positive electrode is mercury and the negative electrode is the amalgam of cadmium. Okay, so and the electrolyte which is used here is the solution of cadmium sulfate. So you can also see that cadmium sulfate is, which is here, it is acting as the electrolyte, and the paste of mercurous sulfate is placed on the top of the mercury. Okay, so this is the mercury, and this is the paste of mercurous sulfate which is being placed at the top of this cell. Okay, so the cell reaction which generally takes place here, it can be written as okay, so this is the cell reaction. The EMF of this cell is 1.01864 volt. Okay, and the EMF of the cell also changes with temperature. It drops by about, so you can just write that EMF changes with temperature, and it drops by about 40 microvolt per degree Celsius. So 40 microvolt per degree Celsius. So just to avoid this this change in temperature or this change in voltage of the cell, what we do is we put the cell in the oil bath. So the cell is kept in an oil bath to control its temperature. Okay, so if the temperature will not be changed, then the EMF also will not be changed. So the change in temperature will remain within 0.01 degree Celsius. Okay, and if we talk about the life of the cell, so generally the life of this cell is about 10 to 20 years. Okay, so this is about this cell. Now there are also certain precautions which have to be take care of, like the mercurous sulfate which is present in the cell. It is actually sensitive to light, and therefore it should not be exposed to light. Okay, and one more thing is that saturated cells should always be kept in an upright position. This is due to the reason that because if they are tilted, there is always the danger of mixing of electrode materials, and therefore these cells cannot be shipped. Okay, so these are the things related with this primary standard of EMF, which is the saturated Western cell. And one more thing, that the EMF of the cell changes with temperature, that we just discussed that point. The equation can also be written which relates the EMF to temperature. It can be written as this: ET equals to E20 minus 46 into 10 raised to the power minus 6 T minus 20 minus 0.95 into 10 raised to the power minus 6 T minus 20 whole square plus 10 into 10 raised to the power minus 9 T minus 20 power 3. Okay, so this is the equation which relates the EMF with temperature, where this ET actually represents the EMF of the cell at any temperature T, and this E20, this relates the EMF of the cell at 20 degree Celsius. So this is EMF of cell at 20 degrees Celsius, and this is EMF of cell at any temperature T. Now we come to the next standard of EMF, which is the secondary standard. Okay, so this is the secondary standard for voltage. Okay, so this represents an unsaturated Western cell. So this is considered as a secondary voltage standard. Okay, now this secondary standard or the unsaturated Western cell, if we talk about its construction, so it is similar to a saturated cell as we had just discussed previously, except one point, that it does not have the cadmium sulfate crystals as those were present in the saturated Western cell. So those crystals are not present here. So it will have the same electrode, and the solution will be maintained at the temperature of 4 degrees Celsius. Okay, and one more addition here is that porous plugs are used in this case. Porous plugs are nothing but the retaining member which is used over each electrode. Okay, so porous plugs which is the retaining member. So these porous plugs is used over each electrode. And the function of porous plug will be to hold the material in the in its place. So that is why, due to this fact, these cells are considered portable. Okay, so we have discussed one point in the primary standard, that these cells are not portable due to the fact that there is a danger of mixing the electrode materials if we just try to move it from one place to another. Whereas in this case, due to the presence of these porous plugs, they are considered as portable. Okay, so generally the unsaturated Western cell has a shorter life than a saturated type, and the life of a cell also depends on the kind of treatment the cell has received. Okay, so you can just write it down that it has a shorter life than saturated cell. Okay, the temperature coefficient of this unsaturated cell is less than that of a saturated cell. So the temperature coefficient okay, it is minus 10 microvolt per degree Celsius. Okay, and it has an accuracy of about 0.005%. So it can be used for most purposes without the temperature correction. And one more thing, that the working range for the unsaturated cell is in between 4 degrees Celsius to 40 degrees Celsius, that is it should not be operated below 4 degrees Celsius or above the 40 degree Celsius, because uh, uh, sometimes it is seen that beyond these limits, that is the extreme upper limit of reliability occurs at 50 degrees Celsius. So, and below 4 degrees Celsius the EMF drops rapidly and the electrolyte freezes. Okay, and above 40 degrees Celsius the cell material start to melt and the voltage will drop sharply around 55 degrees Celsius. So that is the reason that the cell should be operated in between this range. So normally it is recommended that the normal operating temperature should be about 25 degrees Celsius, and the cell should be mounted so that they are not exposed to extremes of temperature. The EMF of this cell lies between 1.0180 to 1.0194 volt. So we can say that each cell must be calibrated against the primary standard in order to know its exact EMF. So obviously, since this is the secondary standard, so it must have to be calibrated against the primary standard. Now we come to the next type of the voltage standard, which is the laboratory standard. So this is the laboratory EMF standard. Now this is actually a Zener diode based laboratory standard, which you are seeing here, this figure. Okay, and you can see that there are different things, like this is the supply voltage, this is the Zener diode, this is the resistance. So this supply voltage E, this supply voltage which is represented here by this E, this is usually higher than the Zener voltage of the diode, which actually assures the breakdown of the diode. And the resistor which is present here, that is this resistance, it has a high value and it is placed in series with the diode and the battery. So it actually serves the purpose of limiting the current through the diode during the breakdown. So this has the purpose of limiting current through the diode during breakdown. Okay, so because due to all these semiconductor devices such as Zener controlled reference sources, they actually have replaced the standard cells in generally in different industrial applications. Okay, and you know that in industries we have the laboratory standard. So this is one type of, you can say, the standard which can be prepared. Okay, so this is a circuit containing the this voltage source in series with the resistance, then Zener diode. Okay, so when the supply voltage varies for any reason, so most of this variation is taken up in the voltage drop across this R. Okay, so what this will do is there will be a very small change in the diode current, and as a result the reference voltage remains practically the same. Okay, so this can be understood as the laboratory standard of EMF. Now you come to the resistance standards. We have discussed the voltage standards. Now we will discuss the resistance standard. Okay, now the circuit which you are seeing here, it actually shows a typical standard resistor, and the resistance wire which you are seeing here, that these are the resistance wire which are just in the sideways. Okay, it is also written here as resistance wire. So this resistance wire actually it is made from alloy, and that alloy can be this manganese. Okay, so this is an alloy, so the resistance wire is made from this alloy. And generally if we talk about the composition of this alloy, so it has nickel of 4%, then it also has copper as 84%, and it has manganese having 12% component. So you can see that the most of the content is actually copper, but some amount of manganese and nickel is also presented in this alloy manganese. So it has the property of high resistivity, low temperature coefficient, low thermal EMF. Okay, so these are all the properties of this alloy. Okay, so you can just write here that it has the property of high resistivity, okay, then low temperature coefficient and also low thermal EMF. So the resistance of the standard at any temperature T, it can just be given by this equation RT equals to R25 plus alpha T minus 25 plus beta T minus 25 whole square. Okay, so this R25 actually it is the nominal value of resistance at 25 degrees Celsius. Okay, and alpha and beta are the coefficients. So these are thermal coefficients, this alpha and beta. So you can just write it down that these are thermal coefficients. Okay, this alpha and this beta. So the value of alpha is generally 10 into 10 raised to the power minus 6, and the value of beta is minus 0.5 into 10 raised to the power minus 6. Okay, so this is the resistance standard. Now there are also certain errors in these resistance standards, like the error due to the stray inductance and capacitance, the error due to the skin effect. Okay, and one important you can say error is the error due to the contact resistance of the terminals, especially in case of low value standards. So in order to reduce this error due to the contact resistance, what we do is that the contact resistance can be reduced by using a 4-terminal construction. Okay, so 4-terminal construction means that 2 terminals are called as current terminals, and whereas the remaining 2 terminals are called the potential terminals. So while using this 4-terminal construction for the resistance, the current is passed through the 2 outer terminals which are called current terminals, and the voltage reading is obtained from the inner 2 terminals. So those 2 inner terminals are called the potential terminals. Okay, so for accurate measurement, actually the current drawn from the inner terminal must be kept to the minimum. Okay, so we'll also discuss this 4-terminal resistance separately. Okay, so this was all about the standards related to the EMF and resistance. So we've discussed some standards for EMF, and we discussed the standard for resistance as well. So from the next class we'll try to see the next topic. Thank you very much.